Check it out now, y'all.
nanoHUB-U, online instruction.
Well, it's week 5 already, and those of you that have hung in there with me in the course know something about how these very small transistors operate, the essential physical principles. What we're going to do in week 5 is to talk about a few other things. We're first of all going to talk in this lecture about how small we can make a transistor. In the next 2 lectures, we'll talk about a couple of other kinds of transistors. We've only been talking about silicon MOSFETs, but the basic principles that we've been discussing apply to other transistors as well. So we'll do that in lectures 2 and 3. And, devices operate in circuits. And in order to really understand how to design devices and why we're worried about things like on current and off current, we need to understand a little bit about the circuits that those devices operate in. So we'll discuss that in the final 3 lectures of this week, and then that will wrap up the course. So the topic today is fundamental limits, and let's dive in. This is a plot that I came across about 10, 12 years ago. It's a plot of the number of the feature size of a transistor versus year, and the numbers here are referred to the numbers of transistors on a chip at each point in time. And when you plot this on a log plot, log of the feature size versus year, it's a straight line since the transistor was invented, basically. And the trends are transistors get smaller and smaller, and we put more and more of them on a chip. Now, in this particular case, right around the beginning of the 1990s, actually several times during the course of this evolution, we'd stop and ask ourselves, how much longer can this go on? How much longer can we continue to shrink devices? I was involved in a workshop about the year 1999 where we were approaching 100 nanometer feature sizes. And people were very, very concerned. That's why this line here is starting to taper off. There was great concern that we wouldn't be able to scale devices below 100 nanometer channel lengths and other feature sizes. Okay. Well, what happened? This is plots of the number of transistors per microprocessor chip. It's Intel data from 1970 till the current time. And you can see that the number of transistors on a chip just continues to increase along a straight line that is known as Moore's Law. So Moore's Law is an observation that was made in the 1960s by Gordon Moore. And Gordon Moore observed that every year the number of transistors on a chip doubled. And he made the prediction that this would continue for a while. Now, it's slowed down just a little bit. The number of transistors on a chip doubles every technology generation, which is about 18 months now. But when you plot this on a log scale, it looks like a straight line. And this exponential growth in transistor density is what's driving the electronics industry and has been going on for a long time. Now, you really don't appreciate what's going on here when you plot this on a log plot. The big questions are, how many more years can we continue to shrink? That'll extend that straight line a few more years. But to really appreciate what's going on here, we need to plot this data on a linear plot. So let me just stop and make an observation here. My first job was an MOS process engineer, and I started that work in 1974 on a 5-micron N-channel silicon process. 5 microns is 5,000 nanometers. And what we're talking about now is how far can we push this? The big challenge is, can we get to 5 nanometers? So, tremendous amount of progress has occurred over my own career. And as I was saying, you get a different sense of what's going on here by plotting these numbers not on a log scale, but on a linear scale. This is the same data published on a linear scale, or plotted on a linear scale. And what you can see here is that it looks like until about the year 2000, nothing was happening. This was the time when we thought Moore's Law had almost ended. And when you plot it on a linear scale, you can see that the number of transistors per chip just continues to rise very, very rapidly. And that's what the big question is today in transistor scaling is, how much longer can we do this? Now you might ask, why are we doing this? Why do we keep shrinking these devices? And the reason we do that is because there are lots of benefits to doing that. So you shrink the size of each device, you get more and more of them on a single chip. That's what we call Moore's Law. And that does all kinds of wonderful things for us. It reduces the cost per function because all of the electronics is on one chip. We don't need multiple packages that have to be assembled. It increases the speed because we don't have wires to going off chip and connecting various chips to slow things down. It lowers the power because we have everything on one chip, and multiple chips increase the amount of power. So we can enable things like laptops and cell phones with reasonable battery life. And the compactness and everything, and the new functionality that you get when you continue to reduce things, denser and denser memories, better and better images to take better pictures with your cell phones. This scaling has really what's powered electronics for the past 40 years or more. And it's sort of a big question about how much longer can device scaling continue to power electronics. Now, when I was beginning my career, we were just learning how to shrink devices. And there was a very famous paper that was written by Bob Dennard at IBM Research at the time, which sort of explained to all of us how you go about shrinking a device. So the idea is we'd like to take a device at some dimensions, and these are the basic IV characteristics in the linear region. So this looks familiar to us now. We've been discussing this. And what we want to do is to scale it down by a factor kappa. Okay, if we reduce the size of the device by a factor of the square root of 2, all of the linear dimensions, then we reduce the area by a factor of 2, and then we can put twice as many on a chip. That's Moore's Law. And what we would like the electrical performance to be is a scaled version of the bigger device. So we shrink the width of the transistor, we shrink the length of the transistor, we shrink the thickness of the oxide all by the same factor, we shrink the power supply voltage by the same factor. And if we do everything carefully and properly, we'll end up with the current just shrunk by the same factor. So here's an example in this paper. This is for kappa equal 5. This is a 5 micron channel length MOSFET, the kind that technology that I was developing in my own very first job. And this is what happens if you scale it by a factor of 5. So you reduce all of the dimensions by a factor of 5. You have to reduce the junction depths by a factor of 5 to manage the 2D electrostatics. You have to reduce the depletion widths by a factor of 5. How do you do that? You reduce the doping density by a factor. Here they did it by a factor of 2, and then you reduce the power supply voltage by an appropriate factor, and you end up shrinking the depletion width as well. And if you follow the rules that Dennard set out, then the IV characteristic of your larger device, which is well behaved and has nice transistor characteristics, the IV characteristic of the smaller device is just a scaled version. The larger device had 15 milliamps of current. The device scaled by a factor of 5 has 0.3 milliamps of current. So if you do all of these properly, you can continue to shrink the devices down. Instead of a 20-volt power supply with the large device, we have a 4-volt power supply with the smaller device. And this kind of scaling is what has powered the industry. It's gotten very formalized. So the semiconductor industry gets together and maps out this scaling very carefully. You can see how all of this is done at the International Technology Roadmap for Semiconductors website, where they lay out all of the dimensions. If you look here at one of these tables, this is 2012. The physical gate length is 22 nanometers. That's where we are today. And you can see that they're mapping out this downscaling of channel lengths all the way to year 2026. And they're trying to identify what has to happen in order for Moore's Law to continue. If there's a yellow box, it means, we don't quite know how to do this yet, but we have ideas. We think we can make it work. If there's a red box, it means that we really don't know how to achieve this at all, but we'll have to figure that out in the future. And this has been going on for several years and is really helped the industry continue Moore's law scaling. It's interesting to read this document, so I encourage you to spend a little bit of time with it. You know, one of the things that you'll notice here is that when they're specifying device parameters, there's a line here for bulk MOSFETs. That's a MOSFET on a silicon wafer with a semi-infinitely thick silicon layer. And you can see it stops at the year 2017. And then fully depleted SOI continues a little bit longer. And then multiple gate or FinFET type structures takes over and continues. So there's an expectation that the transistor structure is going to have to change. So there's an expectation that the traditional bulk MOSFET is going to have to change to something like this FinFET type structure, where you wrap the gate around the channel in at least 3 sides to get better control of the gate electrostatics and better 2D electrostatics, lower subthreshold swing, lower dibble, all of those things. So electrostatics is a big challenge. And there are many other issues too, and some of them sound rather mundane, but they're very, very challenging. You have a metal contact to the source and drain. That means you have some resistance. As you scale all of the dimensions down, that contact hole gets smaller and smaller. So the resistance gets bigger and bigger. And if the resistance is large compared to the resistance of the channel, then the performance suffers. The gate electrode and the drain electrode are very close together, closely spaced. So the electric field lines from the two will form a parallel plate capacitor. That's a parasitic capacitance between the input of the device, the gate, and the output of the device, the drain. When you put a capacitor between the input and the output of a transistor, it's especially bad. So these parasitic effects, as you get smaller and smaller, are also important factors that challenge scaling. Another one is variation. When the device gets very, very small, it's subject to a lot of variability. In fact, the channel is getting so small that the number of dopant atoms in the channel is countable. And it will statistically vary from one transistor to another. And that introduces variability in the threshold voltage that makes it difficult to design a chip when you have 1 billion transistors with different threshold voltages. So lots of challenges, but lots of bright people that have been addressing them, and Moore's law is going to continue for another decade or more. But eventually we will reach some fundamental limits, and that's the subject of the lecture today. Now, one of the fundamental limits is illustrated here. These are some quantum transport simulations, and what you're seeing here is the conduction band of a MOSFET with high drain voltage in the off state. So there's a large barrier between the source conduction band and the drain conduction band. The color here indicates the energy at which the current is flowing. So red indicates high current. You can see that when we look at a 13 nanometer device, channel length device, that's half the size of state-of-the-art technology today. The device still operates like a conventional MOSFET, just the way we've been discussing. The current flows over the top of the barrier, put a positive gate voltage on, push the barrier down, we get more current that can flow over the top of the barrier. If we scale down to 10 nanometers, you can see it's basically still operating in the same way. If we scale to 7 nanometers, now you can start to see some current tunneling quantum mechanically underneath the barrier. And if you go to 4 nanometers, the electrons just tunnel completely through the barrier. The barrier appears transparent almost to electrons. The electrons don't know there's a barrier there. Since a transistor operates by controlling the barrier with a gate voltage, it's very difficult to make a good transistor when you get down into this situation. So that's an illustration of the kind of fundamental limit that can arise. And that's what I want to talk about in this lecture, just the fundamental limits, some very simple ways to get a handle on what are the fundamental limits of a MOSFET. The practical limits are very, very important, but what we're going to discuss in this lecture are the fundamental limits. So let's look at our little cartoon of the energy band diagram. In the off state, there's some barrier that prevents electrons from flowing. If we apply a drain voltage, we have a bigger barrier that prevents electrons from going back in the wrong direction. I'm going to use an approach here that's similar to this particular paper by Viktor Zhirnov and his colleagues. I do it in a little bit different way, but we get the same answers in the end. So that's our off state. What happens in the on state? You apply a positive gate voltage, positive potential pushes the energy down, the electron flows from the source to the drain. Once the electron gets in the drain, it scatters and dissipates all of its energy and drops down near the bottom of the conduction band, and the switching event has occurred. Okay, so let's ask ourselves a set of questions. First question is, what is the minimum energy it takes to switch, to convert a 1 to a 0 or a 0 to a 1? So what we'll do is we'll look at this situation where we've turned the device on, an electron flows from the source to the drain, it dissipates in energy and drops down. Now we have to require that the electron doesn't hop back over the barrier and go back to the source. If it does, a switching event hasn't occurred. Now, you see this occur many times in physics, and we've talked about it earlier in the course. The probability that an electron will hop over an energy barrier is e to the minus barrier height over kT. So that probability that an electron then hops back over is e to the minus barrier height over kT. And if I speak very fundamentally, that probability has to be less than a half. I have to have less than a 50-50 chance that the electron will return to the source, or I don't have a transistor. Of course, in practice, I'll need it to be much less than 50%. But we can get a fundamental limit by saying it's 50%. We can solve for that minimum energy, and that minimum energy turns out to be kT natural logarithm of 2. It's a very small energy. That's a very fundamental limit that you can get in very many different ways. You can get it from thermodynamic arguments. The way we've gotten it here, it's some very specific arguments from a very specific device. Okay, let's have a look at the minimum channel length. What's the shortest that we can make this? Now, let's assume that somehow we can manage the electrostatics, so we can control the 2D electrostatics. So we're worried about quantum mechanical tunneling. How thin can this barrier be such that the electrons don't have a significant probability of tunneling through it? Well, fundamentally, we could say that that probability has to be less than a half. There has to be less than a 50-50 chance that the electron will tunnel through, or we don't know that we're off. This is, we can take a very simple treatment of quantum mechanical tunneling using something called a WKB approximation. That if you've had a basic quantum mechanics course, it's one of the first things you discuss. And we can estimate what that probability will be, and it goes exponentially. Higher the barrier, the smaller the probability is, exponentially with barrier height, and exponentially with barrier width. So we get this simple expression from an approximate quantum mechanical solution. That probability needs to be less than a half. That means that the channel length has to be longer than some critical value to make that probability small enough. This is how long the channel length has to be. So you can see the minimum channel length then is h bar over square root of 2m times the energy barrier. And if I take that energy barrier, if I arrange things so that that energy barrier here is equal to the minimum switching energy and no larger, then I can express the minimum channel length in terms of the minimum energy. And I get an expression like this. It's not material independent. Depends a little bit on the effective mass, but only as a square root of the effective mass. All right, then I could ask for minimum transit time. How long does it take the electron to zip across from the source to the drain? Well, that's just the length, the minimum length, divided by the average velocity that the electron is flowing. Okay, the average velocity, well, let's assume that it just comes in with the unidirectional thermal velocity. So this is our familiar expression for the unidirectional thermal velocity. Then I can throw away a couple of constants that are on the order of unity, and I'll get a simple expression h bar over the minimum switching energy. I can express these kTs and things in terms of the minimum switching energy that we derived earlier. Okay, so the result of those very simple arguments is that we get some limits that appear to be quite fundamental. We've done them specifically for this barrier-controlled cartoon model of the MOSFET. We determined that the minimum switching energy is kT log 2, And that's a very fundamental quantity that we can get from many different arguments. We have an expression for the minimum channel length in terms of that minimum switching energy. We have an expression for the minimum delay time in terms of that minimum energy. And one thing I want to point out is that you could get these same expressions from these two quantum mechanical uncertainty relations. That's how Zernoff and his colleague did it. And that kind of makes you think that these limits that we've derived for this very specific device are maybe more general. Maybe they apply to any switching device, no matter how we make it. All right, so let's take a look. My numbers are a little bit out of date. 32 nanometer technology. Today we have 22 nanometer technology, but we can get some sense as to where we stand. So here's our fundamental limits. Put in some numbers. Let's just use m rest mass of an electron for the effective mass. We get a minimum channel length of 1.5 nanometers. That's really small. We get a minimum switching time of 40 femtoseconds. That's really fast. We could say if the area of a transistor is proportional to the minimum channel length squared, we could produce a density of transistors that would be enormous and sort of unrealistically high. Another way to get a density of transistors that's more reasonable is to say how much power dissipation on a chip can I cool at reasonable rates and at reasonable expense. So if I do standard things, I can cool about 100 watts per square centimeter. If I go to esoteric, expensive cooling, using liquid channels flowing through the chip, we can maybe get close to 1,000. But if I use 100 for more typical products, that would translate to 1.5 billion transistors per centimeter. If we just go to the International Technology Roadmap and pick off numbers, you can see that in terms of switching energy, we're much bigger than the fundamental limit. We're 2,500 times. And once you put in all the complexities of circuits and all the parasitic capacitances and everything, you really get even an order of magnitude or more higher than that still. So in switching energy, we're a long ways from fundamental limits. Channel lengths, though, we're beginning to push down. We're getting within an order of magnitude, and we'll likely go considerably closer. Delay time is also about 15 times or so the minimum time. And the density of transistors is really about as dense as we can make them and still not dissipate more than 100 watts per square centimeter. All right, so that's sort of a sense as to where things stand. This is one of the big questions these days that everybody is asking is, what is the future of Moore's Law? How much longer can this go on? What do we do after we've shrunk transistors to the smallest dimensions that we possibly can? Is there another device that operates on different physics that allows us to continue to make transistors smaller and smaller? If you're interested in my own particular take on this, which is a few years old now, 2003, I can point you to this article in Science. But one of the things that I think is going to happen is that, Moore's Law is really about lowering the cost per function, putting more and more electronics on a chip at roughly the same cost and enabling more kinds of products and more kinds of capabilities. We do it by making transistors smaller and smaller and putting more of them on the chip. There are other ways to do that. One can add a diversity of devices and add new capabilities. One can stack devices by 3D and do all kinds of other things. And more we're going to see us doing those kinds of things to continue the progress in electronics after another decade or so when we've scaled devices as small as we can possibly make them. Okay, so that's a brief look at fundamental limits. We'll switch gears in the next lecture and talk about a different kind of transistor. Thank you.